Headlines about failed robot deployments often scream one thing to viewers: bad software. We assume the artificial intelligence simply glitched, a logic error in the code that caused a machine to stumble or drop an order. But this narrative misses the real story entirely. The robots didn't fail because their brains were broken. They crashed because their bodies couldn't handle physics. In high-stakes environments like restaurants, failure isn't a coding bug. It is a fundamental mechanical limitation. Today we unpack why autonomous systems cannot yet replicate human dexterity and adaptability in unstructured spaces, revealing the hard engineering reality behind the silence of these failed deployments. Consider what happened with major restaurant chains in Guangzhou that recently shut down their robotic waiter programs. The headlines focused on the rollout failures, as if the robots had lost their way or misinterpreted a customer's order due to poor language processing. In reality, the autonomous navigation systems were functioning perfectly fine. These machines could follow precise paths and locate tables with high accuracy. The collapse came from the physical interface itself. Robots in these deployments frequently spilled soup and dropped food trays because they lacked the ability to maintain steady grips on unstable objects. They possessed a super-intelligent brain inside their chassis, but that intelligence was trapped behind hardware that simply cannot modulate force like human skin can. This reveals a critical gap between navigation and manipulation. While autonomous movement is becoming a solved problem for many systems, fine motor control in chaotic environments remains the single biggest bottleneck. A robot can navigate a crowded dining room without hitting a chair, yet it fails when asked to carry a bowl of hot liquid across that same floor. The issue lies in tactile feedback loops. Unlike human hands, which constantly adjust grip pressure based on friction and weight shifts felt through millions of nerve endings, current robotic actuators operate with significant latency between sensing a slip and applying corrective force control. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Without advanced haptic systems comparable to the sensitivity of human skin, these machines cannot dynamically modulate their grasp strength. If an object shifts slightly under load, a soup bowl sliding on a tray, the system often reacts too slowly or applies incorrect torque. The result is either hardware damage from crushing delicate items or product loss from dropping them entirely. This creates a scenario where software logic works flawlessly, but the mechanical execution fails under real-world stress because the robot cannot feel what it is holding with anything close to human precision. This leads us to a counterintuitive finding regarding how humans actually perceive these failures. A 2024 study from the University of Nevada, Reno, funded by the National Science Foundation, revealed that user trust in robots is not destroyed solely by errors, but by how those errors are handled and perceived as mechanical versus logical. When a robot physically fails due to dexterity limits, users lose faith instantly if they believe it was just stupid software making mistakes. However, the data shows something surprising. When the system explicitly acknowledges its physical limitations or admits an error state transparently during interaction, user trust can actually increase compared to when a black box AI makes silent logic errors. The study indicates that human operators are far more forgiving of mechanical failures if they understand the robot is trying but physically constrained rather than assuming it is incompetent due to bad code. This suggests that the path forward isn't just better algorithms. It requires robots that can communicate their physical state effectively while we solve the underlying engineering bottlenecks. The failure in Guangzhou wasn't just about dropping food. It was a failure of expectation management, where users expected human-like adaptability from machines built for structured environments. We are currently hitting a wall where software intelligence is outpacing hardware capability. You can have an advanced language model inside a robot that understands every customer request perfectly, yet still spills your coffee because its gripper lacks the force control of a human thumb and forefinger. The bottleneck is mechanical, not computational. Until we develop better tactile sensing arrays, variable stiffness actuators, and faster haptic feedback loops, remote physical assistance will remain limited to highly structured environments like warehouses where objects are predictable and floors are clear. The engineering horizon for successful customer service robots lies in solving the dexterity gap. This requires moving beyond binary open and close grippers towards systems that can sense texture, weight, and slip with millisecond latency. It demands hardware architectures capable of mimicking the adaptive compliance of human tissue rather than rigid metal claws. Until these physical constraints are addressed, no amount of AI training will allow a machine to serve soup in a crowded restaurant without spilling it. The future of embodied customer service depends on building better hands and skins before we try to give them smarter brains. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.